Okay, so today we're going to be coding the wave equation. This is going to be done in stock Python and with very easy math. And with stock Python, I can run this program on my Windows XP laptop that can't get any new libraries anymore. So this is what the wave equation looks like. We're going to be using something a lot more simple than this. But the left side of the equation basically says that the speed of the wave squared, which is c, like the speed of light, times the curvature of this wave is equal to the acceleration of the wave. But instead of that equation, we're going to be using something much simpler. This is called Hooke's law. If the blue ball was sitting at the wall initially, and then you pull it away from the wall, and assuming it's attached to a string, then the force is equivalent to the k times d, where d is the distance it's pulled away, and then k is a special value for the spring, where something like rubber would have a really low k value, or something like steel that's really stiff would have a really high k value. And this is what we use to simulate the zero-dimensional version of the wave equation, but now we're going to be doing it in one dimension. So it's going to be a whole entire line of those points all being connected and pulled together. Now imagine the wall was replaced with two individual objects on the left and the right, and we're going to have a focus particle in the middle of it. Now if the objects on the left and right are equidistantly spaced from the object in the middle, then the object in the middle won't have a favorite of which side to be pulled left or right. It only will want to be pulled up and down. So basically we're just adding the two forces from the ball on the left and the ball on the right. If you take the k value multiplied by the d1 value, that's the amount of force that the ball on the left wants to pull the middle ball up. Now you can see how the object on the left and the right are both positioned above the center object, so they both are trying to actually pull the center object up, which then causes an acceleration. So by the equation F is equal to k times d, which creates forces, we also know that force is equal to mass times acceleration. Now if we associate the springs with an imaginary k value and every single one of these objects with an imaginary mass, and then you can combine the forces from the spring on the left and the spring on the right, and then rearrange the equation to have an acceleration is equal to some other stuff. This stuff is the same equation that we saw earlier, where k divided by m is equal to the speed of light squared, and then the two distances put together is actually the curvature. And then acceleration was also that other weird looking partial derivative thing. And then once you have acceleration, we can easily convert that to position after you have velocity and stuff. Okay, so we're going to be using the built-in library called Tkinter to show the graphics of this program. So I'm going to import the Tkinter library first, and then also I'm going to be using the sine function later, so I'm going to import the math library as well. And then I put the linspace function in a file right next to this file so that I can use it. And I don't have to code it, I can just call the function and I don't actually have to ever type anything down. Alright, so now we're going to set up the canvas from Tkinter. This is how you open up a window, and then we need to name the window, and then name our window that's called root wave equation. And then root.geometry 500 by 500 dictates how big our window is going to be. And I'm going to create a canvas on top of this window, and I'm going to name the variable graph. And some of the arguments, I really don't know what they do, but the first one is the window we're going to be putting it on, which is our root window. And then the width and height, I honestly have no idea what they do, but then the BG is the background color. And this graph.pack function, I honestly also don't really know what it does. Okay, so now to actually start coding the wave. To start, our wave is going to be comprised of a linspace function where we can have a number of particles all evenly spaced out initially. So I'm going to start with 100 particles, where n is equal to 100, so that's 100 particles, a is equal to 0, which is going to be the very left side of our wave, and b is equal to 100, which is going to be the very right side of our wave. And I'm going to create the x coordinates of our wave with the variable called x. So now from our linspace function, we have the x coordinates of our wave. And these x coordinates for now are just not going to change. And now we need the y coordinates to be initially set up. So I'm going to make an empty vector of y, and we're going to fill in this y vector with the y coordinates of all of our points that we want it to initially be at. So I'm going to call a for loop in the same range of 100 of what our n was. But just to make sure that we have the same number of y and x points, I'm going to put the range of the length of the x vector. And now it's time to start adding stuff into our y vector. I'm going to make it a special sine function that I know is going to have a 0 point at both the start and the end. And I'm going to make it have an amplitude of 50. So I put the 50 in front of the sine, and then inside the sine function I put pi divided by 10, so that every multiple of 10 I know what's going to happen to the sine function. Now I want to multiply this by the x value at every single position, but I can't just multiply it by x, I have to multiply it by x of I, which would be the current position along the x vector. This doesn't really matter, you can just make it whatever you want, honestly. We also need a velocity of y at every single point, so that later on we can integrate our acceleration to turn it into velocity, and the velocity we can turn that into position. And it's going to be the same for loop, and then I'm going to start the initial condition of velocity to be all zeros at every single point. Now I'm going to make up an imaginary k value for these little tiny imaginary springs, as well as our imaginary mass. I'll set k equal to 1 and the mass is equal to 10. These don't really matter. And then now let's make a while loop so we can start calculating this differential equation. I put while true just so it can run indefinitely. The way we're going to be visualizing this differential equation is with 99 little tiny line segments connecting all these imaginary points, these point masses together. So inside this while loop, we need to write a for loop that goes 99 times. And then inside this range, we put the length of x minus 1. because we don't need to make a line segment that goes outside of our points. We only need to make 99 in between. And then the create line function is from Tkinter, and then we need to base it off of our graph, which is our canvas that we're drawing on. And then the create line has inputs which go by the first point's x and the first point's y, and then the second point's x and the second point's y. And then also the color of the wave and then the width of the wave. So first we need x of I to be our first x point, and then comma y of I. And then we need to connect this point to the very right of it, which is going to be x of I plus 1 and then y of I plus 1. And then fill is going to be the color, and I'm going to pick blue. Tkinter doesn't really have that many colors you can pick from, but it has some. I think you can find the color list online somewhere. And then the width is just like the pixel width of the line you're drawing, so I'm going to name mine as 2. And now we need to start updating the y positions of all of our particles along our wave. So this is where the math that I just explained comes into play. So now we need to write a for loop to calculate the positions of every single particle along this wave, which is going to be based off of its initial condition and then the acceleration of all these points, and then which affects the velocity, and then the velocity affects the position. Now if you put this inside the range function, you're going to be calculating the correct number of points. Now we need the d1 and the d2, which is the two displacements of the particles on the left and the right. So this gets the difference of positions of the focus particle and the particle on the left of it. And I did it the wrong way, but you can just put a minus sign on your forces later on. It doesn't matter which way you subtract the values out, because it's just a difference in displacement, really. Now we have the two displacements, we need to calculate the force. Now this is where the negative value comes in. So force is equal to negative k times the two displacements put together. Now we have the combined force of the imaginary springs on the left and the right together. And then to convert from force to acceleration, you take acceleration is equal to force divided by the imaginary mass. And now we know that acceleration affects velocity, so the velocity of our exact particle in this point in time should be added onto itself, which is basically integrating it, but you don't just add the acceleration. We need to take acceleration times dt, which dt is just going to be a small increment in time. So you take acceleration, multiply that by time, and then you get velocity. So let's say that the velocity is equal to itself added on a times the dt. But we never created the dt variable, so let's put it up above. Now you want dt to technically be as close to 0 as possible, but that would be really boring to watch our program do that. So 0.25 is good enough, and you're going to see what the problem of it is when we start running the program. And the same thing with how velocity is affected by acceleration, your position is also affected by the velocity. And we're going to be using the same way to get the position as we integrated from acceleration to velocity. So we add on to our current position its velocity times its time increment. So basically if you're standing somewhere and you're going at a certain velocity, you multiply the time times your velocity that you actually went, and that's the total distance that you just accumulated onto it. And that's the basics of an integral. Now we need to update our screen, so root.update is how you update the Tkinter screen. And then graph.delete all will make sure that we get a new screen every single time, so we're not just going to be pasting a bunch of lines on top of each other. It's going to write a line and then get the old ones out and then write new lines, and it's going to look better that way. Now if you run this exact code, you're going to get your first wave equation simulation. But that doesn't look good. So we have a few things to fix this. First of all, let's add on some pixels to the x and y coordinates so we can have this wave in more of the middle of our screen. So I added 100 pixels onto both of the x coordinates and 250 onto the y coordinates. The reason why I added onto the y coordinates is because you're actually counting pixels from the top of your screen downwards. So if you add on pixels from the top of your screen, you're actually going to be going downwards, whereas the x coordinates just go from left to right. Now you can see that a lot better, but we still have a big problem. It gets really big out of nowhere and we don't know why it's happening. Now the reason that's happening is the dt should technically be an infinitesimal point, but we're not actually using that. We're using 0.25. So that's not exactly like 0.00000 to infinity and then a 1 on the end. So basically what we're doing is trying to approximate a curve like this, but then every single point that we travel, we're going to be missing it and having an error of some sort. So by the time we get to this point, we know we should be going flat again. And so our little guy would actually just travel this way. And then by the time we're out here, we would also calculate it again and probably go somewhere out here trying to follow the slope of this. But if we only evaluate the slope at certain time intervals at like 0.25 seconds, then our approximation of the solution is going to be off. That's why we're going to be overcalculating our wave equation every single time we run through the while loop. So to fix this, I'm going to put some imaginary air resistance onto it, which wasn't the original wave equation that we just looked at. It's a little bit modified of the same exact wave equation. You just put another term onto it and you multiply some coefficient multiplied by the first derivative of the wave with respect to time. So I'm going to call it friction force, FF. Then I'm going to start off with the imaginary friction coefficient. I'm going to call it 0.3, and this could be any number you want, depending on how thick you want your every single particle to be. It might slow down in the air faster, it might slow down in the air slower. But I'm not going to be writing this exactly like you would expect an air resistance equation to look like. I'm actually going to be writing it so you can still have a linear partial differential equation, so you can really solve this by hand in a way. Now we have a friction coefficient 0.3 multiplied by our velocity of that particle and that instance of time. Now you would expect to see this velocity velocity squared, but again, I'm just going to keep it normal and linear. We're just trying to fix this over approximation error again, so this works good enough. And for the later on simulations that we're going to be doing, we're really just looking for the shapes of waves, so that we're not really looking for the exact solution that you should be with calculus. And that looks a lot better, and it slowly decays our wave down to 0. Since just because of that air resistance, it should slow every single particle down over time. Now, if you make this friction coefficient too small, like 0.1, then our wave will grow to infinity again. You just have to make sure that your friction coefficient is just big enough so that your wave does not grow to infinity. So 0.3 or 0.31 does work great for this particular simulation with the values of m and k that we picked. And a really common thing that you would do with these wave equations is create boundary conditions, like the left and right verymost points. You would want to take them and shake them up and down a lot and see what would happen to your wave. So I'm going to take y of 0, which is our very leftmost point, and I'm going to make it act as if it's a sine function with respect to time. So I'm going to make the very left point shake up and down and see how that affects the rest of our wave with the given initial conditions that I gave it earlier. So I'm going to make the sine wave 100 plus a 70 amplitude wave. I'm going to make it pi divided by 200, and we need to multiply this by a time value. I'm just going to call this time value j for right now, but we need to create this j. Since this is going to be representing time as j, we need to set it as 0 before our while loop starts, and then every single time we go through this while loop, we need to increment it by 1. Now the j goes up by 1 every single time the while loop goes through another time. Now you'll see how our friction affects the wave over time. Our initial condition just decays to 0 as our driving force on the left side of this wave takes over, and it just takes over completely to where you can't recognize the initial condition because we put that friction on it. Now this is just the introductory videos to this wave equation series, so I'm just going to make one simple example of the pulse wave, what you would typically see in Wikipedia or something like that if you look up the wave equation. So we're going to run this same sine wave, but only if j is less than 200. And so if you know trigonometry, you know what the sine function does at 200. It goes to its maximum point and then it goes back to 0 whenever j hits 200 again. But I want all of our initial conditions just be 0. So all of our old stuff, just get rid of that and then set all of our initial y positions, all 0 initial velocities, and then also get rid of the 100 plus because we want the sine wave to be based off of 0, not based off of 100. If you have some really long line or something like a closed line sort of a thing, you can pluck the end of it and it'll do the same exact behavior as what you're looking at right now. But obviously without the air resistance, then it should just keep on fluctuating from the left to the right over and over and over again for infinity, but we put the air resistance in there so our program doesn't blow up every time. The next time we're going to be making the same program, but graphically it's going to look a lot cooler. And remember, do not subscribe.